Hi, Albert here. In the last video, we moved from looking at finite shapes to looking at infinite patterns in the plane, still though with a focus on their symmetry groups. So what changed? Well, we looked at the houndstooth pattern and we noticed immediately that there's a big difference there. There are infinitely many symmetries. So writing down the entire symmetry group is no longer possible, or at least no longer easy. So how can we make sense of the symmetry group? How can we possibly now say whether two patterns have the same symmetry group if there are infinitely many symmetries? Well, we can use our intuition for a start. Let's take a glance at these two. Obviously, they're different patterns, but there are some similarities here. For example, some of their symmetries are the same. Both of them have a translation upwards as their symmetry, and both of them have a translation to the right as one of their symmetries. In fact, these patterns only have translational symmetries, no reflections and no rotations. And every translation can be written in terms of the upward translation TU and the rightward translation TR and their inverses. TU inverse, which is a translation downwards, and TR inverse, which is a translation to the left. In other words, the symmetry group of these two patterns is generated by TU and TR in both cases. Since they have the same generators, exactly the same generators, their symmetry groups must be exactly the same. So our job in general is simple. If we can understand the generators of a symmetry group of a pattern, then we can represent the symmetry group much more easily and compare it to other symmetry groups more easily as well. Before we dive into analysing the symmetries of patterns properly, let's remind ourselves of the possible isometries of the plane, and along the way, we'll probably investigate the relationships they have with one another. These symmetries are not all equal. They have varying levels of power, as I like to say, where a symmetry is more powerful if it can be used to generate more different kinds of symmetries. We will go through them from least powerful to most powerful, and I'll explain what I mean along the way. So first, the least powerful is the translation, which we'll denote with a T, perhaps with a subscript if there are two different translations, like here T1 and T2. If we combine two translations, we always get another translation, but we can never get anything else. So this is the least powerful. Next, we have the glide reflection, denoted with a G. The glide reflection, if repeated twice, will always result in another translation. For example, here, G squared equals a translation upwards, T. What kind of isometry do we get if we combine a glide reflection with a translation? I'll leave that one for you to figure out in the exercises. The next kind of isometry I want to talk about is the rotation, denoted with an R. Rotations are interesting because if you repeat them over and over, you eventually get back to where you started, in contrast to the glide reflection and the translation. In this case, this rotation R repeated 6 times brings you back to the identity, so R to the 6 equals identity. If we combine two different rotations, for example here R1 and R2, we here get another rotation, which we can call R3. Sometimes, however, combining two different rotations gives us a translation. For example, in this situation, if we combine R1 and R2, we get a translation. Finally, the reflection, which we will denote with an F for flip. Combining a reflection with itself gives the identity, but it is most powerful when combined with others. For example, these two reflections combine to give a rotation around their intersection point. And these two reflections that do not intersect, when combined, give a translation. Is it possible to combine several reflections to give a glide reflection? Again, you can have this one as an exercise. Okay, so let's get back to patterns and how to work out their symmetry groups. In fact, let's look at an example. This pattern has every kind of symmetry: translations, reflections, rotations, and glide reflections. What is the best way to work out a set of generators for this pattern? The key is to first find a suitable tiling for the pattern with a fundamental domain. A tiling is just a division of the pattern into pieces of the same shape and size. And a fundamental domain for the tiling is a tile such that every different symmetry of the pattern maps the fundamental domain perfectly onto another tile. So how can we find a tiling with a fundamental domain? The easiest way is to draw on all of the symmetries. For example, in this case, if we draw on the lines of reflection, it carves the pattern up into tiles, and these tiles map onto other tiles by symmetries of the pattern. So these are all fundamental domains. Let's single out this tile, though any other choice would also be perfectly fine. Here are some examples of things that aren't fundamental domains. For example, this region tiles the pattern with translational symmetries, but a reflectional symmetry does not map the domain nicely onto one of the other tiles. This other region has symmetries of its own, so again is not a fundamental domain. In general, we may need to divide further after marking on the reflectional symmetries to account for rotations and translations, for example. We will see an example later and more in the exercises. For now, let's stick with this example and see why the fundamental domain is so useful. Any isometry must take the fundamental domain to another one of these tiles by definition. And because the fundamental domain has no symmetries, there is only one way that the symmetry can move the tile there. It can't, for example, move the tile there and then rotate it, or the pattern wouldn't match up. So this wouldn't be a symmetry of the pattern. Additionally, from our theorem back in week 1, an isometry is completely decided by where it takes 3 points that form a triangle. And so there is exactly one isometry that takes the fundamental domain to each given tile. In other words, each symmetry corresponds to a unique tile, the tile it takes the fundamental domain, and each tile corresponds to the unique symmetry that takes the fundamental domain there. So there is a one-to-one correspondence between tiles and symmetries. For example, this tile corresponds to the reflection in this line. This tile corresponds to a rotation around this point, and this tile corresponds to a translation. So, to find a generating set for the symmetry group, we just need to find a generating set of symmetries that can be used to take the fundamental domain to any tile. Then we have definitely got all of the symmetries. Okay, it's best to try to use the more powerful symmetries as generators, as they can be used to generate more symmetries. The most powerful symmetry is the reflection, so let's try those first. If we consider just the reflection in this line, call it F1, we obviously can't generate everything. In fact, we only get 2 symmetries, the reflection F1 and the identity id. You can see that because using these reflections, we can only map the fundamental domain onto 2 tiles, this one and this one. So we certainly need one more at least. Let's add in this one here and call it F2. What symmetries can we generate now? Pause the video and have a think. In fact, we still can't do very well. If we repeatedly use F1 and F2, we see that we can only map the fundamental domain to places inside this hexagon. So we can only generate a finite number of symmetries, certainly not all of them. F1, F2 is in fact a rotation around this point here where the reflecting lines intersect, as we have previously discussed. Therefore, we need to add another. Let's go with this last reflection bordering the fundamental domain. Now we can combine these two to get a rotation, F2, F3, and we can combine this rotation to get more rotations, R2 squared, R2 cubed, etc. If we combine these 2 rotations together, we can get even more symmetries. For example, we can get a translation up and to the left, and we can get a translation downwards. Now it is pretty clear that we can get every single tile from this fundamental domain and these 3 reflections, and therefore we can get every symmetry. Therefore, the symmetry group is generated just by the reflections F1, F2, and F3. So we may write the symmetry group as F1, F2, F3 in angle brackets. Looking at the pattern, there are clearly many more symmetries than just these reflections. But since these reflections take the fundamental domain to any tile we like, we know that all the symmetries of the pattern must be generated by these 3. The reflections really were powerful. We managed to express all the rotations, glide reflections, and translations just in terms of them. To recap, the strategy is to firstly find a tiling and a fundamental domain, a tile with no symmetry which can be used to build the entire pattern using the symmetries of the pattern. Then, we begin to add in symmetries, starting from most powerful to least powerful, until we can use those symmetries to move the fundamental domain onto every tile in the pattern. We can then be sure that we have found a generating set. Let's look at a couple more examples before I let you have a go yourself. This example from earlier has no reflections, no rotations, and no glide reflections, and the translations are generated by the horizontal translation TR and the vertical translation TU, remembering that we are allowed to use the inverses of the generating elements when generating symmetries. To see that this is definitely correct, note that this is a fundamental domain, and we may take this fundamental domain to any other tile using a combination of these two symmetries and their inverses. So the symmetry group is TU-TR. This example is a little harder. There are two obvious reflectional symmetries, which chops the pattern into squares. However, the tile that this creates has a rotational symmetry, so this is not a fundamental domain. Instead, we should split this tile further into 4 pieces. Now we add generators, working from the most powerful symmetry to the least powerful. 1 reflection F1 is obviously not enough, as before. 2 reflections F1, F2 are still not enough. Adding in the rotation finishes the job. Notice that we may combine reflections and rotations to get a translation in both directions. Therefore, the symmetry group is F1, F2, R1. This example is interesting, as it is also generated by 3 reflections, just like our first example. However, their symmetry groups are clearly different. The first example has a rotational symmetry consisting of a 60-degree rotation, and the second one does not. This means that though the generators look the same, F1, F2, F3, the relations between the generators are not the same, showing that the symmetry group is different. There is an exercise on the class website linked below with more details on this. Wow, that was a lot of examples. We have seen how to figure out the generators of a symmetry group by looking at the fundamental domain and trying to map it onto all of the other tiles in the pattern. It seems still like there are many types of symmetry groups that a planar pattern may have, but in the next video we will actually see that the total number is in fact very small. Before you move on to that though, please have a look at the exercises, where there are plenty of opportunities to try out your generator finding abilities. After you've done that, I'll see you in the next video.